There has been an amazing progress in the deep learning field regarding generating images or text, which are mainly powered because of the huge annotated datasets. However, in robotics we face a different situation, where annotated data is not abundant and each lab works with different embodiments. In this work, we propose ImitationNet, an unsupervised human-to-robot motion retargeting model that does not require annotated data and codes with the different embodiments via shared latent space. Imitation learning is a long-standing challenge in the robotics community. Teaching human-like robot motions is time-consuming and usually requires expert knowledge. Retargeting human motions to robots is an efficient and generalizable solution for skill transfer and natural interaction. However, prior works fail to retarget the human motion accurately to robots, or require extensive manual annotations of humans and robots in the same pose. Considering all these limitations, we propose an accurate and real-time deep learning model called ImitationNet that learns how to retarget human motions to control this Tiago robot without ever seeing a human-robot pair. That's it. Very simple. And despite I know that we all want to see the results, let's first talk about our problem. Motion retargeting is a task that aims to translate a given motion from domain A, for example the humans, to domain B, for example the robots. For that, we propose to build a shared latent space between the two domains where similar poses are positioned close to each other while dissimilar poses are far away. While this task seems a typical translation problem, there is an issue. We do not have an annotated human-robot motion pair. That means that we do not have the correct translation between humans and robots, and therefore we need to 1. Learn where humans and robots have similar poses in an unsupervised manner, and 2. Translate then any human pose to the same pose in the robot, accounting for the difference in embodiments. In fact, the result is a benefit as non-living data allows to extend our world really fast to any robot. Okay, but now how do we really do it? First, we adopt an adaptive contrastive learning that autonomously builds a shared latent space between humans and robots based on a relaxed similarity metric. We define a simple but effective rotation-based similarity metric to assess how close two poses are. Basically, we compute the distance of quaternions between common body limbs. Indeed, this is a relaxed measure that we only use to assess, given two poses and an anchor pose, which one is closer to the anchor or farther away. Therefore, we construct these positive pairs of poses, which we show in this example as greens, or the negative pairs in red, where the robot poses are more different. During training, we randomly sample any triplet of poses, can be the human or robots, to build this shared latent space. First, we use the triplet loss from the contrastive learning to push together the poses from the positive pair and push apart the representations of the negative pair. In these cases, Q represents our multi-layer perceptor and encoders for the human and the robots. In reality, the goal is to decode these human poses into similar robot poses. However, as we do not have these human-robot pairs, we propose to decode the previously encoded robot pose. This reconstruction problem allows us to ensure that the latent space can be decoded accurately to robot poses. In fact, as we previously encoded similar human and robot poses to be together in this space, we should be able to now decode also a human pose to a robot pose. But at this point, D, the MLP decoder, has only seen robot data. To encourage the human retargeting to be accurate, we additionally propose a latent consistency loss. Any human pose projecting the latent space is decoded to a robot pose and encoded back to a latent space, optimizing this reconstruction. With this trick, we enforce the consistency of the latent human poses after being decoded to a robot, thus ensuring that we capture the essential information of a human in the robot decoder. The composition of these three losses results essential at the end to build a robot latent space in an unsupervised manner, while ensuring the high quality and smoothness of the retargeting. In the inference time, the process is very fast and simple. We can drop the robot encoder and just encode the human pose and decode it to a robot choice directly. To understand our approach, let's go to see some results. First, to fairly compare our approach with the baselines, we manually annotate 11 human-robot pairs with pose correspondence. We train and evaluate both our model and the baseline and compare the mean square error of the joint angles between the predicted and ground truth robot poses. You observe a big improvement in performance while being 3 times faster. We additionally evaluated our model under different training conditions and observed the benefit of our proposed losses. Additionally, we wanted to show how our approach can highly impact the robotics community. Now, thanks to ImitationNet, one can control any robot from text, RGB data, or simply by generating motion between two desired poses using our work. First, by using text-to-motion models, one can control a given robot via text commands. The generated human poses are retargeted to a robot, which is directly controlled from the textual command. In these videos, you can see different examples of the text-to-robot control. We also implemented a self-collision avoidance full body controller to ensure the reliability of the retargeted poses in the real Tiago robot. Take a look. Nice, right? Secondly, we observed in the experiment that our V-latent space can really capture the similarity of embodiments. Thanks to this property, we are able to provide two poses, either human or robot, to our model and decouple the trajectory from one to another by simply interpolating in the latent space. You can see here in the results. Thirdly, the robot can imitate the human motion directly from observing RGB videos. We use a pre-trained pose estimator module to extract the human pose from RGB videos, and then our imitation net can directly control in real time our robot. These videos showcase the efficiency and accuracy of our framework that allows the robot to move, navigate, and even act as a human. We propose ImitationNet, an unsupervised human-to-robot retargeting method that ensures an accurate retargeting without any paired human and robot motion dataset. Our model allows to control in real time the robot motion in Tiago in a collision-free way from various modality commands, text, video, or condition by key poses. We tested our work in the real Tiago, achieving high-quality performance. That said, please visit our website and check our paper for impressive results. If you have any questions, contact me or any other authors. And thank you so much for your attention. Bye bye.